Good morning.
Good morning, Ms. Allen.
Today we're going to talk about volumes of revolution. It's our last new topic. This is the last thing you're going to learn in AP Calculus AB. It is sad. It is sad. If you can see through your tears, we'll keep going. Maybe. Okay, so yesterday we did volumes with cross sections. We took an area, and what did we do on top of that area?
Gave it depth.
Yeah, we gave it depth, and we gave the depth a specific shape. So we stacked semicircles on top, or triangles, or squares on top of this area.
I can't see your hand.
You can't see my hand motions? Okay, they'll live. Today we're going to talk about volumes of revolution. So I want to start sort of with the same shape that we started with yesterday. Let's say that we have this area. What did we do with that area yesterday? Yeah, and how would you describe giving it depth? Yeah, we stacked shapes on top of it and made a solid. What we're going to do today, instead of stacking shapes on top of it, we're going to rotate it. So I want you to imagine that area coming out of the page and rotating, so towards the front of the classroom, then back behind the smartboard, and then back to where it started. Can you see what that would make?
It's like hollow.
So it's not hollow because we're actually, that area shaded it. A cone sort of thing, like sort of a bowl. Do you see that? And what would each, if we were to slice it, what would each cross section be? Would it be a semicircle?
Yeah, quarter circle.
So actually, I have a video. Let's look and see. Maybe. So here's this shape. And what I'm going to do is pull it out of the page and back around. And so it looks sort of hollow, but we're actually going to let it create a solid. And then I think it's going to turn it for us. I hope so. The person's talking in the video, but I'm going to be your video. So look at each cross section. What is it? It's a circle. It's a disc, we call it. And we'll talk through all the notation that they're using. But yeah, so there's a disc, and there's the radius of the disc. Okay, yeah, that's what I want. So can you envision that now? With this one, we're pulling this out of the board, and each cross section is a disc. What's another word for a disc? What shape is a disc? A circle. How yesterday did we find volume? What do you do to find volume?
Based on height.
Integrate what? The area. You integrate the area, and what's our area always going to be if we're rotating around an axis? It's always going to be what shape? A circle. It's always going to be a circle if you do a circular rotation around the axis. So we know that our volume is going to be the integral of pi times my radius squared. What we have to figure out is what's the radius. So if we were to take that shape and rotate it all the way around and make a circle, can someone actually come up here and draw the radius on there? This is where everyone volunteers because I'm videoing. You got me? Okay, so come up and draw. If I were to rotate that around, what would be the measurement of one of the radiuses, one of these discs? Yeah. Good. So that's one radius of one circular cross section. What would be another one?
Just keeps going down.
Yeah. Perfect. So do you see how the radius changes? Thanks, Jay. How would we describe what the radius is if this is the function f of x? Yeah, it's just your function height. Your radius is just your function height, top minus bottom. And that's the radius of your circle. And so if we call this from A to B, our volume is just going to be pi times the radius squared. Usually I pull the pi out. I take my radius, which is my function. I'll call it r of x instead of f of x. Squared dx. And I'm letting my x values go from where to where? A to B. So there's your volume formula. You just have to find the radius of your disk and then pi r squared, integrate it to give it that added dimension. I can also do a vertical axis of revolution. It's the same idea. I'll draw a different function. So maybe some function that looks like this. But I want to rotate around the y-axis. If I'm rotating around the y-axis, so coming out of the board and moving to the left around the y-axis, what's going to be different about my radius? It's going to be perpendicular to the y-axis. Good. So do you see that this is your radius if you're rotating around that horizontal axis? So if we're trying to determine the length of that, we're going to have to be in terms of y. Whatever function that is, we're going to need to describe it in terms of y to show how far left and right it goes. But still, it's the same idea. We'll say this is a y value of A, a y value of B. It's just pi times your radius squared y. So that's the theory behind what we're doing. It's the same thing. We're still integrating area to get volume, but every single cross-sectional area is what? It's different, but what shape does everyone make? A circle. So it's always pi r squared that we're integrating. And we just have to figure out what our radius is. Just like yesterday, to save you writing stuff down, I have the examples printed. So you can use these examples here. Do you have anything you want to say to the class, James?
Why better having fun on your field trip?
That was kind of
They're
it.
not on their field trip.
Well, if you're not on a field trip, I hope you're having fun and not doing calculus.
No, they're doing it.
But it's impossible to have fun not doing calculus. So
True.
shame on you.
Your YouTube channel's gonna blow up.
You think so?
Did you get them a copy of the examples?
I'm going to post them online so they can print it out or come by after class and get a copy. But if they hear my instructions to do that now, it'll be too late.
Shame on you, Adrian. You're not coming to class today.
We hope you're playing beautiful music to the old people. They probably can't hear it. I shouldn't post this on YouTube. This one's going to be unlisted. This is why I'm disabling comments on my YouTube channel.
It's also going to be a lot longer than 30 minutes.
Okay, focus. Find the volume of the solid formed by revolving the region bounded by f of x equals the square root of sine x and the x-axis from 0 to pi about the x-axis. Whew, what do you think we should do every time? Draw a picture. What does the square root of sine x look like?
Like this.
Yeah, so it still looks like sine x, but what kind of values can you not plug in?
Negative.
Yeah, so you can't plug in values for x that make sine negative. But between 0 and pi is sine positive? Yeah. And so it still looks like sine. If we plug in 0, sine is 0, 0, so the square root of 0 is 0. If we plug in pi, sine of pi is 0, so the square root is 0. If we plug in pi over 2, sine of pi over 2 is 1, the square root of 1 is still 1. But what happens is just a little bit steeper. So it still looks a lot like sine, just a little bit of a different height to the curve. So this is the area that I have. And I always draw an arrow. I'm rotating it around which axis? X-axis. So my radius is going to look like that. How would I describe the height of that radius, the value of that radius? Top minus bottom. What's on top?
One.
Is 1 always on top? It's the square root of sine x. It's your function height that's on top. And what's minus the bottom? What's the bottom? 0. So it's just your radius, just the square root of sine x. And that's all we need is a radius. Then to find our volume, we integrate pi r squared, so root sine x squared, with respect to x. What x values do I go between? 0 and pi. And so that'll give me the area. What kind of shape is this going to make? How would you describe it?
It's like a wide circle.
Yeah.
It's a sphere.
So not a sphere.
It's like a.
It's like an
pound
egg.
cake.
Like a pound cake?
It's like an ugly.
No, that's how you're going around like that.
Yeah, if you went around like that, it'd have a flat bottom. But is there any flat side on this?
It's like a.
No.
No. So if we're rotating this way, coming out of the board and background, you see how it's sort of like an egg?
I was going.
Oh, it is kind of like an egg.
Or like a churro.
Yeah. Okay. For your homework and for a lot of your tests, I'll let you math 9 that. But this is actually pretty easy to do by hand, so let's practice. If we were to solve this one, how should we simplify it?
Sine x.
It's just sine x. What is the antiderivative of sine x? Negative cosine x. I'm going to put the negative out here because I want to. Plug in pi and 0. What is cosine of pi?
1. Negative 1.
Oh
Sorry.
my gosh, this is on YouTube. You don't even know what cosine of pi is.
I'm really sad.
What's cosine of 0? 1. So I have negative pi times negative 2. So the volume is exactly 2 pi cubic units. Isn't that pretty?
Indeed, it is not.
I think so too. Let's do another example. Find the volume of the solid formed by revolving the region bounded by 2 minus x squared and 1 about the line y equals 1. I don't even know where to start with that until I do what? Draw a picture. So we have axes. 2 minus x squared is a downward opening parabola shifted up 2. And g of x equals 1. So horizontal line at 1. Do you see this region bounded? I would always go ahead and shade in that region. And then, like I said, I always draw an arrow with what axis I'm rotating around. So what am I rotating around? I'm actually not rotating around an axis. I'm rotating around this line. What kind of shape is that going to make?
An egg again.
A smaller egg, another egg. I don't know if it's actually smaller, but my diagram is smaller.
Well, we'll just see when we find the area. won't we?
I would also draw what line you're rotating around, and I literally draw in my radius every time. Can you see your radius? It's from the edge of your area to your axis of revolution. How do we describe the length of this radius?
It's
Top to the top.
Top minus bottom. So on top we have 2 minus x squared, and on the bottom we have 1. Let's simplify that into what?
1 minus x squared.
1 minus x squared. So our radius is 1 minus x squared. And once we have that, we can just use the volume. We're integrating each little disk, pi radius squared. And what x values do we want to go between? How can we figure those out?
Plug in your,
Plugging X.
So this time we can't plug in x.
you find
Set
where.
them equal.
Set them equal, find where they intersect. So 2 minus x squared equals 1. X squared equals 1. And so x equals what?
So that's-
Plus or minus. Could you do that by hand? Yeah, that's not hard at all to do by hand. Oh wait, what did I forget?
Oh, you've got the square.
I got the square. That's super important. Now it's harder to do by hand. What would you do if you were to do it by hand? You got it, Jay.
What's the word?
Foil. You'd have to foil it out and then integrate each one. But I'm too lazy. So we're going to math 9 and see that it's 16 pi over 15.
It's pretty neat.
Cool. Questions so far about that? I love these. I think they're really fun. I got a nod from Luke. Why don't you try this one?
Pause the video.
I'm just gonna let the video. Yeah. They can fast forward if they want.
Well, you can pause it.
You can pause it when we're done. You can pause
Yeah,
it.
because there's like a stop button and there's a pause.
Do you want me to pause it?
Yes.
Who wants to instruct them to pause the video now and try this?
I already
Jay, you
did.
got it.
Pause the video now while we work this problem out, and when you unpause it, I'll do it for you.
Welcome back.
Thanks, Kevin. So here's your solution. If you rotate this, what shape does it make, Zane?
Cylinder.
A cylinder. Good. So you could just use your cylinder formula, but we integrated and found that the volume was 75 pi. This next one is actually sort of interesting. If we take this same exact area, but rotate it not around the x-axis, but around the y-axis, does it make the same volume? It's the same area. Does it make the same volume? You try and see.
Pause the video now and try to rotate it around the y-axis.
Thanks, James.
Welcome back again. We missed you.
So we see here that we're rotating around the y-axis. What kind of shape do we make, Zane? Cylinder. But even though we have the same area that we're rotating, do we make the same volume?
No,
No, why not?
because it's a fatter cylinder.
Yeah, so what has more of an effect on volume, changing the radius or changing the height?
The radius.
The radius, since we're squaring it. So whichever one has a bigger radius is going to be bigger. Cool. Let's do number 4 together. Find the volume of the solid formed by revolving the region bounded by y equals e to the x, and x equals 2, and the x-axis and the y-axis about the x-axis. That's a lot. I don't know what that says. Let's draw it. Y equals e to the x. That looks like this. X equals 2. Looks like that. And the x-axis and the y-axis. So it's this area. It's bounded off by 4 different sides. What are we revolving around? The x-axis for the solid. Do you see the radius? It's right here. How do I express the height of that radius? Top minus bottom. So it's e to the x minus 0. And so once I have my radius, it's just pi r squared. Volume equals pi.
Isn't it just e to the 2x?
Yeah, so we're going to simplify that because that's going to make it a lot easier to integrate, to differentiate. We are going to do this one by hand. What are my bounds, though?
0 to 2.
Perfect. 0 to 2. Let's do this one by hand. E to the x squared, looking like that, I don't really know how to anti-differentiate it, but as James said, we can write that as e to the 2x. This is really good at practice. Don't embarrass me on YouTube. What is the antiderivative of e to the 2x? 1/2 e to the 2x. Why is it 1/2?
Because you bring the 2 down, you differentiate.
Yeah, so you're anti-differentiating. Your error function is 2x, so du is 2. You have to multiply by 1/2. So it's pi times 1/2 e to the 2x. Plugging in 2 and 0. And so we get pi over 2. I'm going to combine the pi and the 1/2. E to the 4th minus e to the what? 0, which is just 1. So that's going to be an acceptable answer. Pi over 2 times e to the 4th minus 1. Questions on that? And last disk. Find the volume of the solid formed by revolving the region bounded by y equals e to the x, and x equals 2, y equals 15. So we still have e to the x. We still have x equals 2. And then we have y equals 15, which is going to be somewhere up here. This is not really the scale. Do you see what area?
Yeah.
This area right here.
Yeah.
And we're rotating around what line? X equals, ooh, not that. X equals 2. So we're rotating around a vertical axis. So how do I draw my radius? Top to bottom or right to left? Right to left. Good. So there's one of my radii. What shape is that going to make?
A little bowl.
A little bowl or an upside down dome. It's going to have a flat top. How do I express this radius? Right minus left. So instead of y equals e to the x, what do I have to use? Good. Natural log of y minus, what function is this on the left? X equals 2. No, it's not, is it? Yes, sorry. Natural log of y minus 2. Right minus left to get that radius. So once I find the radius, then it's easy. I just do the integral of pi r squared, my r, natural log of y minus 2 squared, dy, which means what kind of bounds do I need? Y values. I need to start at this y value, end at that y value. Which one's easier?
The 15.
The 15, because that we can see it's y value 15. What are we going to have to do to find that one? Yeah, y equals e to the x, and we can plug in x equals 2. So what is it? E squared. We can also set equal to each other natural log of y and 2, either way. And that, does that look fun to do by hand?
No.
No. You actually, do I know how to do that? I don't know if I know how to anti-differentiate that by hand. So we let our calculator do it. And I haven't done it, so I don't know what your calculator would say. But there's that. How are we doing so far?
Good.
Cool, we're halfway done. Now we're gonna move away from discs and do washers. What's a washer?
When it washes your clothes.
Yes, that's using the definition, the word in the definition.
Isn't that like something like tools or something?
Yeah, so what is it in tool language? It's got a hole in the middle. So it's a circle with a hole in the middle. And so I want to look, because you eat donuts and you don't want kids to eat a washer. So I have this area, and I rotate it around the x-axis, what's going to happen? When you rotate it, so pull it out of the board and bring it to the back, are you going to have discs? No, what are you going to have? It's going to be hollow. Good. And this is actually, again, easier to see with an animation. So I want you to see what it looks like. I could have drawn a better picture. If we take, this is my favorite animation, square root of x and some line. And rotate that around the x-axis. Each cross section is not a disc, it's a washer. It's a circle with a hole in the middle. So if I wanted to find the volume of this solid, what type, like, how do you think I should do it?
Doesn't it just depend on how thick?
Yeah, it's definitely gonna depend on how like thick they are.
Subtract the area.
Exactly. So what we're gonna do you see how we have an outer disk and an inner disk? So we're gonna find the area of the entire solid figure and then subtract out the part that we're cutting out. Subtract out the part that has no shaded area inside.
So in the other ones that we did, they were like completely filled in.
Yeah, exactly. So what it sort of depends on is your area flush against your axis of revolution? Is it touching it? If it's not touching it completely, you're gonna have a hole in the middle. Does that make some conceptual sense? So same idea, but this time we need to do an outer volume and subtract out the inner volume. So if I'm rotating around the x-axis, my outer radius is going to be, we'll call this top function, so as far away as I get from my axis, all the way down to the bottom. Does that make sense? I'm going to let that entire thing rotate around, and we'll call that big R of x. It's going to be from the shaded area farthest away from my axis all the way down to the axis that I'm rotating around. But then I want to go from the bottom part of my shaded region down to the axis. And that's going to be my inner radius. If I take these heights and rotate them around, is that going to be part of my solid? No, so that's the part that I'm going to cut out. So my inner radius is little r of x. And to find the volume, I'm going to do pi, we'll call this from A to B. I'm going to do my outer radius squared. And that'll give me if I rotated just the top function all the way around. And then what do I need to do? Subtract off my inner radius, which has no area in it. What do you notice about the bounds on those? They're the same, so we can write it as one integral. That saves a little bit of time. 1 pi, a to b, and we can just do rx squared, big radius, minus your little radius squared. Again, I have handouts for you so that you don't have to write down the problems. to find the volume of the solid formed by revolving the region bounded by y equals 4x and y equals x squared about the x-axis. I'm going to draw first. Y equals 4x is some positive sloped line, and y equals x squared looks like this. So this is the area, and I'm rotating it around the x-axis. Is my volume flush against the x-axis? That means I'm going to have a washer. That means I need an inner radius and an outer radius. To get big R, my outer radius, I need to go to the function that's as far away as possible from my axis of revolution. What function is that? 4x. And drop it all the way down to the axis of revolution. So what's the height of that? 4x. To get my inner radius, I need to get to the bottom of my area as close as I can to the axis of revolution and drop it down. That should not touch any area because I'm going to cut that part out. Does that make sense? It's this blank space in the middle. What's the height of that? X squared. And so to find that volume, it's still pi, but instead of r squared, it's big R squared minus little r squared. So big R squared minus little r squared. What are my x bounds going to be? What's my x value here? 0. My x value here is where they intersect. What's that x value? 4. So that's my upper bound. And that's something that you could do with a calculator. No, so washers aren't that hard.
No, I mean, like,
Oh.
doing that.
Oh, doing that by hand? No, that wouldn't be too bad at all. But I'm lazy. Let's do the same exact region. Let's do it about the y-axis. Again, I'm going to do line, parabola. Here's my area. But now I'm rotating about the y-axis. Is it flush against my axis of revolution? No, that means it's a washer. I'm going to need an outer radius and an inner radius. My outer radius, which function is farther from my axis of revolution? X squared. So I'm going to draw from that to my axis of revolution. How do I write that in terms of y?
Oh, where?
That's going to be square root of y on the right minus 1 on the left.
5 x.
0. X equals 0. Does that make sense? Now I need to get my radius that's closer. It should have none of the shaded area in it because I'm going to be subtracting this part out. What's my little radius going to be? 1/4 y. Do you see that if you solve this for x, it's going to be y over 4. On the right, minus 0 on the left. And that's all you need. Then you can set it up. Pi, big R squared, minus little r squared. Again, this one wouldn't be too hard to do by hand, but that's not the point of today. We do need our bounds. What's the lowest y value that I go to? 0. And what's this y value? We said they intersected when x equals what? 4. So what's y going to be here? So 16. So my upper bound is 16. Okay with that? Two more examples. Find the volume of the solid formed by revolving the region bounded by y equals x squared and 2x about the line y equals 5. Here's 2x. Ooh, that's bad. I don't want that. Here's 2x. Here's x squared. So it's the same type of shape. But what am I rotating around now? Y equals 5. It's important to sort of place y equals 5 correctly. Where should I put it? Is it going to be through the area or above that area? It's going to be above it. Those intersect at when x equals 2. So it's going to be above it. This is what I'm rotating around. What do you notice about this area? It doesn't touch at all, but we can still rotate it around. What kind of shape would it make? Yeah, well, I wouldn't really be a funnel. It's sort of more like an inner tube. Like there's literally a huge hole in the middle. Actually,
Touch it all in the
yeah, I think that Wolfram Alpha actually does a pretty decent job. We're gonna try something. If we rotate y equals area bounded, I'm gonna say region bounded. Sometimes Wolfram Alpha can do this. If not, sorry, YouTube. My y equals x squared and y equals 2x around the line. I don't know what all that means. Man, if I had the main version, I could rotate this. I can't. But do you see how there's a huge hole in the middle? It's not connected at all. It's not even connected at the end. So it's just going to be this region with a big hole in the middle. Do what? Yeah, it's sort of like a lampshade. This one for our big R, our outer radius. Which function is actually farther away from the outer radius? Yeah, x squared. So we're going to draw from here all the way up for axis of revolution. How would we describe that height? Perfect. Top minus bottom, 5 minus x squared. And our inner radius is going to be as close as our shaded region gets to our axis. What's little r going to be? 5 minus 2x. And then those are messy. I definitely did not want to do this one by hand, but I can set it up. Outer radius squared minus inner radius squared. And my x bound. What's my lower bound?
0.
And my upper bound is going to be right here. Let's figure out where they intersect. X squared equals 2x, x squared minus 2x equals 0. What does x equal? 0 and. Good? Last one. This one is, so all of these, have we picked up a calculator yet? No. I mean, for evaluating some of them, we'd use our calculator, but we've drawn all these functions without a calculator. This one, you're gonna use a calculator for. You should not sketch it by hand. Find the volume of the solid formed by revolving the region bounded by y equals e to the sine x plus 1 and y equals 5 minus x squared about the line y equals 7. So let's graph all of that in our calculator. Make sure you're in radian since we're using trig functions. Anyone see my other marker? That's not helpful. Okay, so we're gonna graph e to the sine x. Five minus x squared. And I'm going to graph what we're rotating around y equals 7. I'm going to zoom 6 and see if it's what I want to see. Yeah, that's a decent graph of what I want to see. Oh, I think I can draw. Do you see that this is the area that we're rotating?
Yeah, that's how you forgot the plus one on the y.
Oh, thank you. It's e to the sine x plus 1.
Yeah.
And then exponent or to
Yeah.
the side?
Like that. 100% plus one.
So here's the area. And here's the axis I'm rotating around. I should get a digital badge for this. I just want you to know. Look how much digital stuff I'm doing right now. This hurts. Is this gonna be a washer or a disc? Washer. It's not flush against this axis of revolution. There's gonna be a hole. Which function is farther away?
So it's either the
Yeah, so my outer radius is gonna be from here up to here. Big R. What's that distance? What should I be really careful about?
plus
Should I put plus 1 right here? Minus 1, so I distribute that negative or keep it in parentheses. My inner radius is going to be from here to here. What's that distance? 7 minus 5 plus x squared, if we distribute that negative, which if you want to simplify, well, no, I don't care enough. Because I would never do this by hand, I would math 9. So it's going to be the integral pi integral of, oh, I'm not going to be able to do this, 7 minus e to the sine x plus 1 squared. Oh, it's minus 1. Minus e to the sine x minus 1 squared minus 7 minus 5 plus x squared squared. Yes. What am I missing? Bounds. And how do I get those? They intersect. Good. So you need your calculator for all of this. How many decimal places of accuracy do I need? 3. Way to be an overachiever, Jalen. Second, calc, intersect, first curve, second curve, and then I'm going to scroll over to the one towards the left. And I get a lower bound of negative 1.900, so negative 1.9. I need my upper bound, second, calc, intersect, first curve, second curve, and I'm going to scroll over. .206. And then your calculator can do all of that for you using Math 9.
Calculator says,
Calculator says, uh-oh.
I got a negative.
Did you square both of them?
Yeah.
Can I see yours?
Maybe I did the wrong. I think I did the wrong one in the lot.
Oh, you forgot pi, first of all.
Oh, no.
And then your y1. You forgot the 7 minus.
Oh,
That makes sense.
yeah.
But actually, let's let your calculator do this using what James did using Y1 and Y2. If we do math 9, and we can do pi math 9 from, what was it, negative 1.9? And what was my upper bound? 1.2 was 6. And then my first function was 7 minus y1, right? What I have in y1? 7 minus whatever I have stored in y1. I forgot to. I never do this. I usually just type it all in, but it's so much easier to do this. Minus 7 minus whatever I have in y2. Square it. Oh, and my dx or dy? Dx. Even though there are y's in there, but those y's are defined by x's. And that's your volume.
How do you get watch?
If you're ever doing dy, you can just use x instead of y. If you really want to use y, you can do alpha 1. There are y's there. But it works the same way. Mm-hmm. Do you see the little green y above the 1? So that's volumes of revolution. Hey, you're done with AP Calculus AV.
Oh my god.
How does that feel? It is sad. You have a handout. You have something online. I do want to say any last words before we end this video.
Goodbye, friends. I hope you have a good time watching the video.
Like and
Please like and subscribe, leave a comment, and turn on that notification bell.
Is that what YouTubers say?
Say it, Miss
Please like and subscribe. You've seen Math with Miss Allen. Your giveaway is if you come back to see me, I'll give you your homework.
Allen.